Okay. Well, um, thank you very much, Damien, for the introduction, which I'm sure was great. I didn't hear anything. But I'm also very excited to be here. And yeah, thanks for inviting me. Um, this talk really is about, well, Bayesian modeling. I'm sure that was mentioned in the introduction, but also about AI and how both really are powerhouse when it comes to applicability in pharma. So this, what I'm going to talk about is based on a real case study we did together with Roche. And at the end, I will also be showing you a new platform that we're building called Decision AI. So I don't know, what of this was already mentioned, but I'm Thomas Wiecki. My background is in computational psychiatry. I did my PhD at Brown, where I studied how Bayesian models can help us understand complex human decision making. And that work was done with Michael Frank, um, in case anyone is familiar. And while in grad school, I also started contributing to the PyMC project. And that had become one of the most widely used Bayesian frameworks, downloaded over 500,000 times every month, cited in over 3,000 scientific papers. And the success of that, then, of this open source package, has led to me founding a consultancy called PyMC Labs that helps leading companies like Bain, Roche, but also Colgate, HelloFresh, solve some of the hardest modeling problems with Bayesian AI. And across all of these projects, I've seen how powerful Bayesian methods are, from academia to industry, but also really how hard they can be to use. And that's the problem I want to talk about today and how we can fix it. So pharma needs Bayesian AI. It's basically my premise. Why is that the case? Well, there are a couple of principles at play. One is that pharma experiments are complex. We often are dealing with multi-level data, animals in cages, or all kinds of different groups, uh, time varying parameters, structured and longitudinal data. So anything you can imagine, there will be a structure in some of the work that you all are doing. Moreover, usually the experiments are low signal to noise, right? So sparse effects can easily get buried under a lot of variability. And this is where classical methods struggle. And what I mean with classical is usually when, for example, you have a time problem, you start binning things, right? And just like creating features basically that you analyze using frequentist statistics. So with all this binning and slicing and correcting for multiple comparisons, you're losing a lot of power and often missing the very signals you're after. So Bayesian modeling has a very elegant solution to this. And the primary idea is that it lets us map the experimental design directly into a causal model. And then there estimate everything jointly. So we're pooling data across all levels, and maybe even multiple experiments, and then quantify uncertainty in one coherent framework. So that's the promise of Bayes, but also the pain point is still usability. With PyMC, we make it a lot easier, and with the other open source tools, we continue to make it a lot easier, but it still requires well-versed data scientists to use. So to make this all more concrete, I want to walk you through a case study we did with Roche, led by Owen Connor's team, Roche, and of course, special shout out to Damon Rocchero, who invited me to give this talk, and also allowed me to borrow some of his slides that will be with the background. So the preclinical group we were working with is studying developmental disorders. And for that, they use home cage monitoring, where mice are tracked 24/7 with video and infrared video, as well as RFID. So they have a GPS chip just to track all the movements. And then we can just let this run 24/7 and we'll get all the video output. Now, then the question, of course, is what do we do with the video output? So there, Zhan Ping and her group developed a really cool system where they use machine learning to automatically classify behaviors like bar climbing, rearing, vertical climbing. And that gives us, for each animal in each cage, across weeks and across days, we get very rich time series data of behaviors. And I mean, this sounds great, and it is great. So you have a lot less overhead. But nonetheless, now analyzing this data is challenging. Like I mentioned, one way, the classical way usually to analyze this, is by binning things into time. So here we see example data where we see three different animals in three colors. In dark gray is when the light was off, and in white background is when the light was on. And because they are nocturnal animals, you can see how during light off, they move around a lot more. So on the y-axis, we have the RFID, or the just movement tracking over time. So this is basically over 4 days, 2 days and 4 night dark cycles, dark light cycles. And so looking at it from this high level, right? So let's say we wanted to estimate treatment effects. So these were knock-in mice, so genetic modifications, but it doesn't really matter. But note that there are patterns happening at the short time scale, right? One is just light on, light off, but then also, of course, over the course of many weeks, as these mice grow up and we observe changes and different treatment outcomes for developmental disorders. Now, the classical thing would be to say, okay, well, let me just start with binning, right? Let me start with having a light off bin where just like average the activity of maybe each mouse, so all mice together, and then one for light on. And then you need some way of like mapping that into the week structure. So you can do that, and it does work. But there's a couple of things that this approach really leaves to be desired. And already we can see that there's quite a few patterns in this data that we are not capturing if we just had these very wide bins, right? So for example, even with light on in the center column, we see synchronized activity while they're sleeping, right? So one is waking up, they all start to move, and so they have these synchronized behaviors inside of individual home cages. Also, they have a rhythm, right? So they will know before the light turns off and it's time for activity, they will already have an on-ramping time because they anticipate that light is coming on, light is going off. And then also you see them making, for example, a siesta during the day. So all these patterns might carry signal, right? But by binning, we either end up with like very, very crude bins and we don't map any of those things that we have, or we just create many, many bins, right? Which is sort of a question of arbitrariness, but then usually we would plug that into linear models, and then, well, we're dealing with multiple Kelsen issues, right? Because we have all these different bins, or we lose these important patterns. So to summarize this one more time, how it's typically done is you bin data, you run multiple t-tests, and you hope to find signal. But that's fragile. So arbitrary binning decisions make a big difference. Multiple testing and those important patterns are easy to miss. So fortunately, this is exactly the type of problem where Bayesian modeling really shines. And this is basically the project that we did together with Roche, where we built this model. And I'm going to explain some of the properties, we want to stay very high level and more think about what are the things that Bayesian modeling is good at. Maybe you don't care about home cages, but these principles apply generally. So really, any problem you have with a lot of rich structure and like some causal understanding and experimental design, Bayesian model will probably be very powerful. So what we did here was to map the experiment structure directly into the model. So we have mice nested in cages, as you can see on the upper right, and grouped into treatment and control, tracked across weeks. So already there we see that in this experiment, there's a very natural hierarchy embedded. And things can sync on all these different levels, right? Like we already saw that inside of one cage, they are synchronizing activity. And then, of course, there will be similarities between wild type cages and knock-in cages. So all this rich structure we map into the Bayesian model. And we end up with a model that's quite complex. It has it has hundreds of thousands of parameters, right? And we will see where those are all coming from. But it gives us a lot of power. So we don't have the problem of multiple comparisons, and we can simulate designs, what I will talk about for optimizing experimental design and what if scenarios we can run. And we can also reuse priors and use fewer animals. So if we collect, for example, from previous, the wild type responses from previous results we obtained in previous experiments, we can use those. Okay, so now a little bit more detail about the actual model. So like I said, the model is inherently hierarchical that we built. So we map the experiment structure directly into the model. And then here at the week level, we can see really what is happening and over time, right? Now, of course, there's a lot of reason to assume that, for example, between week 8 and the following week, where we have a measurement over multiple days, that there are temporal correlations, right? And if we bin things, we almost always lose temporal correlation. So all that rich structure that is happening at the daily level, at the minute level, also at the week level. So really having notion of time in the model is really critical. So instead of arbitrary bins, we used Gaussian processes to model time. And these models are very flexible, non-parametric Bayesian estimators, usually for smooth curves, right? So whenever you have a smooth curve, and that can be across time, or it can be spatial, then it's a 2D Gaussian process. But they model all kinds of different line patterns. But what's really cool about them is that despite being very flexible, they also can be constrained in very flexible ways. So not only we just like fit any arbitrary time series, but when you can actually go in ahead of time and say like, okay, well, these are the type of time series I'm expecting, right? So in this area, I expect a lot of variability, and in this I don't, right? So you can see where this is going. And the way that we structure these Gaussian processes is via the choice of the kernel function, which just says what type of lines can this model fit and also generate. And this was important here because, like I mentioned, we have data at different timescales, right? So we have the individual movement across minutes, we have the days, and then we have the weeks. And we can construct a Gaussian process model that captures the variability at all these different timescales. So we have a kernel for the short time scale. That's the first inlay. And this is just an example, right? But just imagine like this would be a cyclical seasonal pattern, right? Maybe of light dark cycles. And then we have we can combine that with like a long arching change, which models the disease progression, or just like the developmental trajectory. And then we combine those together into like one kernel. And you can see how we just like basically can layer on more and more basis functions essentially. And then ultimately, though, this will be fit to data, right? So this is just the generative process and how we can combine these kernels. The actual movement of the line, that's going to still be determined by the data. And this is in general a property of Bayesian modeling is it allows you, it's very powerful because it allows you to have a knob where you can really tweak how much structure you want to imbue into your model. So you can either build, um, say, a neural network model, right, that could just like fit anything on like a very general Gaussian process, and or you can build like something that is like extremely narrowed down and just like has all the nodes and very tight priors, and then you just like find basically the right threshold, or the where you want to take that knob. Okay, so here the point is we can with one model model the data at different time scales. And of course, this is also all embedded in that hierarchy I was just showing, right? So this is a hierarchical Gaussian process. So things get pretty wild and definitely estimation is difficult. And now you understand why there's hundreds of thousands of parameters, right? So it's a lot of structure and a lot of time series and parameters. But the model can fit just fine. I mean, it takes a couple of hours and building it was really, really difficult. Um, Luciano Paz is the main developer who built this like absolutely incredible model. And I'm beyond proud of the work that the team did because it really captures so much structure of the of the data. So here we show that we can replicate the behavior in the dashed line with the model in the continuous line for weeks 8 and 28. And then, and this is for a single mouse. And sorry, this is for groups. So this is in blue is for the legends here. In blue is for the wild type, and in orange is for the other one. So just very high level. I mean, there's a lot of things to discover in here, right? But like just focusing back on the high level, where well, we get really accurate replication of the behavior. So all these different patterns are well captured by the model, right? So you can see how the line is going through and able to model all these patterns very flexibly. We get uncertainty. So for example, here in orange, we see like the bar climbing behavior. There's a lot of uncertainty. So some after we switch to dark mode, here in the shaded region, then we see that yeah, there's a burst of activity, but it's very uncertain, it's very variable, and we don't have a lot of data yet. But um, so this is to show that we can accurately model the behavior of these groups at in the short term. So this is over a single day, as well as over the long term, right? So here is a different way of plotting basically how the activity changed from the very first measurement in these two groups. And we also see that we can replicate this behavior really well on that level as well. And it's all, again, just one model modeling all of it together. Now, crucially, it summarizes all this into an average treatment effects over time, with uncertainty shrinking as we get more certain about things. And this type of plot or just analysis is, I think, really powerful because it really allows us to see where the statistical significance is across time, right? So basically, this is, yeah, statistical significance, average treatment effect over time for these different weeks and for different behaviors. So we have the GPS movement data and the bar climbing. And already you can see how, for example, by week 28, we see a big, in the movement pattern, we see a big statistical difference as we turn on the light. So that is, again, looking for effect at that scale. Of course, we can also just go back up to the week scale and then look for uh, trajectory differences at that level. And quickly, because this is just a one single model, we don't have to worry about multiple comparisons. Now that's the core of the model. I want to just tell you about one more cool thing, which is because this is a generative framework, we can go one step further and simulate new experiments, right? So we assume that what we have estimated, the parameters of the model, are true. From that, we can generate new synthetic mice and new experiment runs, and then basically do optimization or whatever other things we might be interested in. So, for example, on the left, we analyzed what happens if we measure fewer weeks, right? So rather than every 4 weeks, maybe it's every 8 weeks or something. And turns out, as you can see with so these are histograms of the effect sizes, essentially, of the movement data between those 3 weeks. And then in color of the line is what subsampling we've done. And we see that they don't change if we have more sparse measurements, which is cool. So, and then of course we can test other things, like what if we have fewer cages, right? So just fewer mice. And then we actually see that the variability is a lot higher between these different runs. So actually having more cages really adds a lot to the stability of your estimates and your ability to measure an effect reliably. So from this, the conclusion is clear. We want to measure fewer time points, but definitely keep the number of cages or even increase. So like I said, this model I think is brilliant and really powerful, and it models all these effects, and it's very rich. But is the model for all its awesomeness being used? Unfortunately not. So we actually did quite a bit of effort to like build a Python package that has Jupyter notebooks of like examples and like going through all the plotting functions and all of it. And that's the best what we could do at that time. And I mean, it's not that like the model is gone, but nonetheless, the PhD student that was working with us on the Roche side left, right? You all know how these things go. And then there wasn't anyone around to like really sort of deep dive into the package and like really use it. And I mean, that that will probably happen at some point, but I think it really highlights a very important limitation of these methods, and that is the usability. So I think now we live in very exciting times because I think we can provide a solution, and that's what I'm very excited to talk to you about. So this effort we call Decision AI, in combining Bayesian modeling with AI to really bridge that last usability gap. And the core idea, as you can probably intuit, is a chat-based interface where you can just ask questions and you get plots and analyses and all of that, driven by an agentic workflow where agents go in and they load the data, they analyze the data, they do feature extraction, inference orchestration, they run the model, they provide input into the model, and then I can explore the outputs. And critically built for scientists, and not only for data scientists, but both should be able to use it. So rather than just tell you about it, I thought I'd give you a quick demo of what this looks like today. Now, this is not fully functional, what I'm showing you. Like this is more of a demo. But we have a version of this that we have showcased and that clients are running on that's that is, yeah, not this version, right? This is sort of the next version that we're working on. So it's packaged here as a web app, but this will be open source, right? So you can run it locally or integrate into your own hardware or work with us to like really get the most out of it. So the idea is to have a very simple interface where you just like ask the main question that you're interested in. And here it's currently set on marketing budgeting because you can run this in all. We've done a lot of marketing analytics work at PyMC Labs, but also in sports analytics, for example. But now let's just run through an example case study of the homepage monitoring that we did. So here the question might be, from our pilot homepage study, when does the disease group diverge from the control group? And now when I click on it, it will kick off the multi-agent workflow and do data prep, feature EDA, running the model. Of course, this is sped up. Running the model usually takes hours, or maybe we had a pre-fit run, but then we get this interface where we now get our initial question and a custom plot created for us based on the model fit and basically the understanding it has of the domain. So one thing that is very critical, we find, is that agents really need to be very tightly well constructed and given a lot of domain expertise in terms of like prompts. So this model, these agents really know everything about homepage monitoring and the model and is able to run the tools and all of it. So that's why it's able to like provide such in-depth analysis. And that's also why it's not just like a general purpose agent, right? So this is an agent that was specifically crafted for this type of analysis and this type of model. So, and here we get like a nice plot that shows us, okay, over weeks, how did the average treatment effect change? And we see, okay, like here at week 10 now, we see that the difference is meaningful. The HDI is excluded, and that's where we see the first divergence. And now maybe I want to ask some follow-up questions, right? So how does the disease change daily activity patterns across different groups, different behaviors? So here then we get another custom plot, maybe some inlay where we can just explore the data, and then we just like keep basically working with it, right? So before I showed you how we can use these generative tools in order to design and optimize trials and experiments. So here we might ask how many animals per condition are needed to detect 20% improvement. And then it will run the optimization and test the different parameters and then give us this table here where it says, okay, how many cages, how many animals per cage, how many total animals, what type of statistical power do we expect from our analysis, and then what's the cost if we have that information included, as well as recommendations. And that is what I think is so powerful about AI is that it is context aware, right? It understands your question, but it can also explain things to you in natural language rather than just like providing you a bunch of plots and or reports, right? Which is like classic what dashboards would do. So there's like a mix of them. We can also like deep dive into the data. So we could just like print the data. So this is basically to show that this so far here is high level, and that sort of the idea is to have something that is available for decision makers that are scientists that maybe don't know all the intricacies of running the model and all of that. But if you want to, right, you can also ask for the code and then basically see it and edit it. Let's say we want 6 chains. And for many of you, this will probably not look like much, but this is basically the PyMC code to estimate this model. And so we can really see what's going on. We can change it, rerun the analysis, and all that good stuff. So yes, there are, like I mentioned, like this different decision packs. So different agents essentially for marketing, budgeting, trade promo. And what's also really cool is once you have these things tied together, right? Um, you can also combine them. So marketing, budgeting, and trade promotion, for example, is something that really needs to know of each other. So by adding more and more workflows into this general framework, we can create very rich um, outputs. So that is what I had. So with Decision AI, we're not just building another statistics tools, we're creating a platform that makes Bayesian modeling accessible, interactive, and decision focused, because I think for decision making, Bayes is the best framework. And of course, if you got a tough modeling problem, you think this tool would be helpful to you, definitely get in touch. We also offer workshops. And if you're interested in the interface Decision AI, what I just showed you, we are early, but we're looking for partners. We already have some, and it would be great to build this together with you and customize it to your models, right? So this, in principle, can run any model. If you just want to dive deeper into PyMC, then this is our homepage. It has a lot of resources. It has a learn section here where basically for beginners, intermediates, it's all kinds of resources and a very rich examples library as well. So this is a treasure trove of just like general techniques and things you can do with PyMC. It's a lot, but you see there's GLMs, different case studies, causal inference, Gaussian processes, like I mentioned. So I also just like scratched the surface of this. Time series models, more classical statistical time series models, GPs can also be used. Spatial analysis. This is a very flexible classifier, mixture models, survival analysis, ODE models, all about the samplers, variational inference, and then also just famous books translated like the Statistical Rethinking lectures, which are excellent, but you also just have the same code in PyMC. So with that, thank you so much for your attention and for having me. If I don't know how we or if we can cover questions, but I don't hear anyone, but I guess Damien could chat, or you can also ask me questions offline. Okay, so the question is, can you provide more details on how Decision AI is using fitted models to answer the questions? For example, is developing the code on the fly given a query? Uh, I don't understand the last one, but in principle, it is using what a data scientist would do. So it has a Python code interpreter running in the cloud, and it basically just like GPT code interpreter, right? Um, so it knows how to write Python code, look at the outputs, and then analyze them. So OpenAI has done a fairly good job with that. Um, but critically, what is missing is one is the rich output, right? So that you have dashboards, and the other one really is the domain expertise and the multi-agent workflow. So there will be an agent that is specialized into um, loading and munging home cage data, right? And then that will pass it on to the um, model fitting agent. And then that might fit the model and it will store that model in a database. So then the next time, maybe we just come, we load the model results, or the agent loads the model results into its Python environment. And then they are just like what we do essentially, or like the data scientist would do, just like querying into the trace, right? And creating custom plots using Plotlib or Plotly that then get displayed. And of course, because AI is getting more and more powerful, the fanciness of these plots can be quite rich. Um, and of course, once you're in this framework, right, and you have all this functionality, it's easy to start dreaming and like, for example, like, well, just now that I have like this analysis, create a slideshow, right? And then it like auto generates a slideshow. And again, this will be not just like random, but because it's all so tightly coupled with the agents, um, you can also just like prompt the agent basically to really create the slides according to your template and how you want to communicate things. Okay, like an example, but obviously that's just an example. Collaboration, like I think there's a lot of richness in this platform approach, and of course integrating with a wider ecosystem, things like MCP, so that you can like pull in your own um, things and your own services, agent to agent protocol. So there's a lot happening and a lot to be integrated with. Next question is about agentic model. How would the agents deal with patient protected data? And now also understand the second line of the previous question. Uh, Developing the code on the fly, given a query. Yes, it's developing the code on the fly. That's exactly what it's doing. Um, right. So, especially in regulated environments like pharma, that becomes important. So there, mainly the data infrastructure, and I would say like data governance is best solved outside of this. So you will want to have your GDPR compliant storages and then connect those to the platform. Or maybe you're using Databricks or whatever. But and there are like many tools that do that, and they can be integrated. Uh, but our focus here is more on like the last mile and really getting the insights, and then it's much more about plumbing, um, and and there, yeah, there's definitely tools available that provide these guarantees that I think you're looking for. That certainly requires special care. Well, thank you, everybody. It's great.